This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good morning, everyone. So, I'm not feeling terribly well. Let's see how it goes. Maybe it's a bit cold, I think. Important topic, though. We will do the supervised learning, which matches with the workshop 2, and the workshop 2 report is due end of this week. I think I extended the submission, and you have been working on it. I will post the next week's slides and the next workshop this week sometime, and I'll make sure that the third and fourth workshops are shorter, so they will be, proportional, because we will have only 2 weeks, and the last workshop's due date cannot be further than the last day of the lectures, because university regulations prevent putting a report due during SWOT-WAC. So I'll make sure that the workshops are proportioned. At least the mandatory parts. I might put some bonus parts, but that's for those who have time and interest. Anything else? So you can see your mid-semester tests during the consultation hours. A lot of people showed up yesterday, and we discussed, if when there are minor issues, we can also address them. But my impression is everyone is happy with their scores in terms of marking fairness. But still you can stop by and chat. The solutions have been online for a while now. And I will also ask the demonstrators to mark workshop 1 reports and post them as well. So that will come as well. Anything else I forgot, or comments? No? All right. Yeah, the supervised learning is one of the most important parts. We mentioned most of the things actually regarding this anyway. I'll start with revisiting linear regression. We have done in between some probability theory, and then you knew it already, but we have adopted a probabilistic view meanwhile. So we can see this bias variance trade-off in light of that. I will also talk about this classical method, logistic regression. I think it gives good insights for the statistical view of things. Then important topic is kernel methods. I will hopefully finish it today. Then maybe start with support vector machines today as well, and then quantifying classification performance. A lot of the things. This is just very informative, very intuitive. I've put very colorful slides to the end of the slide set. You can also read yourself, but we will go over it. Right? Just to refresh our memory, supervised learning focuses on accurate prediction based on given labeled data. So here the key thing is we have not only X, but also labels, which are sometimes Y, sometimes T, depending on which book you are reading, which notation we are using. Using Y is also good. Describing Y conditioned on knowing X, and Y can be a real value, then we have a regression problem. We are estimating a function, or Y could be a label, could be plus 1, -1, or 0, 1. In the binary classification, or it can have a set of values, like, for example, MNIST digits. You have the pictures of handwritten digits, then they belong to one of the 10 classes, right? Digits 0 to 9. So when describing Y conditioned on knowing X, we can also adopt a probabilistic modeling perspective. Then from probabilistic point of view, we are concerned about the conditional probability of Y given X, and of course the data, right? And the model, actually. There is also the inherent assumption here that we adopt the model. So given the data and the model and the X's, I should have put M here probably, right? So because X is the data anyway. or you can see it in different ways. Given a new x, past data d, and model m. So that would be also proper. I put the formal definition here. The idea is, as before, when a new x star, new x comes, that doesn't belong to the training set, you're supposed to do good in terms of estimating its label or value, y, associated with the x. So we are talking about pairs in supervised learning always. Like unlike unsupervised learning, we have only x. In supervised learning, we have the x and y. And as I say, y could be the value of a function, or y could be the label associated with the x. X being the pictures of dogs and cats, then y is the label dog or cat, right? So that's the simple idea. And when we do this prediction, we need to define, we want to make accurate predictions, as you can imagine. We want to make the correct predictions. How do we quantify that? We can define a loss function based on the predicted value and the true value, or a utility function which is minus loss. Of course, the goal is minimizing the loss or maximizing the utility, which is the same thing, right? So we essentially, with this loss function thing, we can turn it into an optimization problem, and we will turn it to an optimization problem. So that's another good connection between optimization and machine learning. This slide is also something you have seen. You're supposed to train on the training set and test on the test set. I'm sure if I ask this in the final exam, there will be a few who will not be able to do this. Then I will not feel bad about failing them. If you don't know this much, I will not pass you. After finishing the subject, you're supposed to know I train on the training set and test on the test set. If you train on the training set and test on the training set, that's not good. That doesn't make sense. And, yeah, as I say. And then, of course, we mentioned our underlying assumption. Future data should kind of have the same characteristics as the data that you have. I had a student, we were doing a machine learning project, and he was not an expert on machine learning, and then he was training things on some data, and then he was using totally different data characteristics to test them. He said it didn't work, and I said, what did you expect? And of course it won't work. You need to kind of have this consistency. The cross-validation techniques, as I mentioned, k-fold cross-validation is the most famous one. So if you have the computational power and time, the trick is you can actually chop your data into pieces and train on the three-quarters of it, and then test on this, and then use the white ones here as the training set, and use this one as the test set. So you do multiple runs, and then you average your performance metrics, right? Each run you get an accuracy metric and loss, then or mean square error, and then if you do multiple runs like this, fourfold is shown here, then that is giving you an average performance. This is the best way of actually using it, doing it. And also there is this issue of, you can also use this cross-validation for determining hyperparameters of your model. That's in addition to the regular parameters that we optimize, there are also these additional hyperparameters, metaparameters, that are part of the model. You can use cross-validation to set them as well. All right, so this is just a refresher of the memory. Any questions regarding these? Yep.
This model is is it clear the previous model is starting on new training for the cross-validation?
No, you use the same model.
Same model, but for the second term, the test part, the validation part is already being tested.
No, what you do is you have the same model. Then what you do is
the wrong two, but
this becomes the test set, and these become the training sets.
yeah, but the test set for the wrong two have been trained in the wrong one.
No, you start from scratch. Yeah, that's a very good question. Thanks for that. Let's clarify this. When you do the round one, you start from zero, and then you train on the white ones and test on the red one, right? And then in the round two, you start from zero. So you do it from scratch. The model is reset, and then you train on the white ones and test on the red one. Each run, you reset the model. Yeah, that's an important aspect. Yeah, Otherwise, yeah, it wouldn't make sense. You're right. You would be training, retraining, and yeah, it would be a mess otherwise. You reset the model between the runs. Thanks for asking that. No, this is just, like when you do you have the data set, right? You divide it into training and test set. If you do it randomly once, yeah, that's one way, but it's not that satisfactory. You do a better job with the k-fold. You divide your data into training and test set in all possible ways, in a sense, or in a more elaborate way. Yeah. And then you take, you take the average performance. You can choose the coefficients that work best, or I don't know, like there's a selection problem indeed. Yeah, that's a good point too. Then you need to select which one to use. All right. Okay, so now let's revisit the linear regression, because linear regression is a supervised learning method, and then we will look at the bias variance trade-off, but with a probabilistic point of view, because we did this least squares without any probability. We just wrote the model as a linear model. Note that the model is linear in terms of the weights, W's, and then the basis functions phi of x, but the basis functions themselves don't have to be linear in x. Phi of x could be a nonlinear function of x, but because this is a linear combination of these phi of x's, this is called a linear model, all right? Not to be confused about. Then we have our data set, and then we have an error metric. If we use these squares, that's the mean square error. You can put a 1 over n here, then it would be the mean. And then essentially, we want to minimize the error because the square term can be written like this. And we have an unconstrained optimization problem unless we impose some constraints on the W's. And then, there could be meta parameters as part of phi. Phi is the model, what basis functions we choose. If we use Gaussian phi of x, then the variance of the Gaussian would be a meta parameter and part of the model. So then when we optimize it, this is regular quadratic optimization. We get this result, and then there are different ways of solving it. Once you write the necessary conditions, because it's quadratic, it's a convex optimization problem. Once you write the necessary conditions, they are sufficient as well. And then once you write these conditions, as written here, it's a set of linear equations that you can solve in different ways. One way is writing as a matrix or invert, but you can also use other methods like Gaussian elimination for solving a set of equations, right? Linear equations. So there's a rich set of methods that you can tap into for this. And then here's an example with cubic polynomial basis. And this polynomial regression, we did it also in the workshop, right? So now let's go switch from this plain non-probabilistic point of view to a probabilistic perspective. So we will make an additional assumption, of course. So let's say we have the training data X and the labels here now the T. Sorry about notation switching, but yeah, it's still obvious, right? So this is a supervised learning problem because we have the data points as well as their labels. That should tell you we have a supervised learning. And we assume that the labels have a Gaussian distribution, and the mean of them is given by the linear regression. So that's the assumption here. The probability of the label given x, w, and beta is given as a Gaussian distribution, which is an assumption here, right? This is a choice we are making here. Then that's a Gaussian with the mean of y of x, w, which is what we had before, and some variance 1 over beta. So this is a nice pictorial representation. So instead of what we were doing was trying to figure out what this red line was based on the data. And that's what we did in the workshop as well. Here, what we are saying is at any point x0, I have this y x0 w, but I'm making a Gaussian assumption here and represent probabilistically what this value will be around the mean. And then if you just plot the mean, it's the same as before, but if this is giving a richer kind of view of this regression problem, right? You will think this is very straightforward, but I have seen people making a whole, living out of this in certain contexts. For example, there is this, for example, is an estimation problem in power systems. The power demand of a house or the city or the state, right? And that's a regression problem. At a given time, what will be the power demand of this place tomorrow? And there are a lot of inputs, past data, but also the weather. What will be the weather? If it's weather dependent, if it depends on other things, it also comes in. And it turns out, they were telling me the whole community only knows this, red line estimation. They tell you a single number. And then there was this guy who told them, oh, by the way, we can have a probabilistic view. Instead of a single number, I can give you a probability distribution. And they went, wow. And, then I said, why is this so wow? But for them, it was a wow thing. So you see, this is knowing probabilities is a good thing, long and short of it. And it makes much more sense to give a probability for estimation. Sometimes, it's better to say tomorrow you will use 335.6 kilowatt, hour electricity. Instead of that, you're saying tomorrow on the mean we expect you to use 336 point whatever kilowatt hours, but we are not so sure. So actually expect the probability of distribution of such. You may get less or more with some probability, right? That's what this image is representing. Make sense? Yeah. So, and that ties up pretty much to this conditional probability, right? This is the probability of what will be the t given this. And then this is the regression version, but you can imagine we can also do the label version of it too. Then it will be just two labels. So if we write it this way and making another assumption that the data is IID generated, then we can actually write it for all the data points, the probability for all the t's and all the x's as a multiplication of these probabilities, individual data point probabilities. And this multiplication is a bit cumbersome, so therefore we take the log likelihood, and then from the likelihood function we go to the log likelihood function for the entire data set and take the log, which makes the product sums, and then exponents in the normal distribution becomes more manageable. Then we get the log likelihood function. And to find W, again, this is an unconstrained optimization problem. As you can imagine, if you take with respect to the W, when you take the derivative with respect to W, these terms kind of don't matter, right? The term that matters is here. Even beta that doesn't matter. This is the same as minimizing least square. So there is actually, we are back to least squares. So this is an interesting connection. So we haven't started with least squares. We made the probabilistic assumption with the Gaussian, and then with the Gaussian distribution, it turns out when you write the log likelihood function and optimize the log likelihood function, I want to maximize the probability that this is I get the right label, most likely label. That is turning out to be the same as the using the least square method as before. So I find the same mean, and the variance is this term. If you take the derivative with respect to beta now, this will become 1. This will become 1 over beta. This will go away, and then equal to 0. Rearrange the terms. You get this, which is 1 over beta ml. Maximum likelihood variance is actually the point variance over the data points over n. So then we get the likelihood function, maximum likelihood function with the optimal values that I have obtained, WML and beta ML, from optimizing my log likelihood function. This is the solution essentially, has the mean as before, but also a Gaussian probability distribution as we assumed, which with the variance as we have computed. Right? So that's you will ask, why should I do Gaussian? Gaussian is the kind of the 101 of first to go of probability distributions, but you don't have to. Like, you can actually make another assumption. If your, for example, if your demand data for power systems is, prior that will have a different distribution of some other sort, then you can actually use that to do the whole trick and find its parameters like this as well. All right? Let's do a question together. And then by using the technique of completing the square, we will use it intermediate step. The question asks us to verify this. So actually, we did the probability of t given w. Now it asks us to, the other one, the posterior distribution p w given t, which will be the Gaussian with some mean and the Sn, the variance matrix, and the mean is looking like this, very complicated, and then Sn looks like this. What we note is what we knew before. Pw is given. We have a prior. We assume a prior on the parameters. We assume they are Gaussian with some mean and variance, and we also assume that we know this, which is what we knew from the previous slide, right? So Pt given this is the y and beta inverse. Then y is, as we said, this is a linear model, so it's W transpose phi of xn. So we know these, and then we try to verify this posterior distribution. So let me go over that. Actually, I didn't want to. I want to give you a bit quicker the solution. It's a bit lazier here, but let's go it step by step, right? What do we have here? We have the from the Bayes theorem, right? We know that we just write the Bayesian rule with the constant. This means proportional, right? This is proportional. So we just write the Bayesian rule, and then we ignore the constant. In this case, the constant that we know, which is the a prior probability of the labels, pt. So we assume either it's uniform or we already know it, so it doesn't make a big play there. And if we write this in full, then we know pt given w. We just substitute this here, right? So let's use that. Clarify this, right? And then for the pw, we assumed this prior, right? So we need to also write that one. So this, we assumed this prior, so it all goes here. Okay? So once we then write them as using the multivariate Gaussian distribution, ignoring the constants, because the constants, we just write, this is the convenience of writing proportional, the constants you can ignore. We have the exponential term here with the mean of this Gaussian is this, right? And the variance of it is 1 over beta. 1 over beta. So therefore, because it's in the denominator, but it's 1 over beta, it comes to the denominator as beta, and then 2 is there. So notice this is written as a matrix. The formula for Gaussian, multivariate Gaussian distribution was in the slides, and maybe you should put it to your cheat sheet, of which you will have 4 pages, 2 sheets in the final exam, so there will be enough space to put that in. So that's the first one. The second one is also here. In this case, it's a matrix, so you write it in this form, S0 minus, right? The other one was scalar, so it was convenient. And the mean is this, therefore this is written like that, again from the definition of the Gaussian distribution. So now we can actually, because these are both exponents and multiplied with each other, so you can actually combine the terms. You get a long expression here. That's why I didn't want to do this, all together, spend too much time on it, because that's not the goal here. So you can actually do it at home as well. When you rearrange the terms, we write it in terms of quadratic in terms of the w's, and then linear in the w's, and then all other terms, also other terms, and then again here W's in terms of W's here, and then additional terms. Now we rearrange the terms and put them into nicer format. Yep, here in terms of W, there's a W transpose and a matrix, and then additional terms that don't contain W, right? So this is just rearranging the terms. And then at this point, the question already gives us the answer, right? So we have Mn given like this, and then Sn is given like this. So now the question gives you the hint, is using the technique of completing the square. At this point, what we do is we add and subtract. Look at here. So we have Sn and S0 inverse M0 plus beta phi transpose T. So that is already here, you see. And then if you put an Sn and minus Sn, if you multiply with Sn here, so we get this. What we do is we add this additional term, Mn transpose Sn inverse Mn. This is a plus, and then you subtract it. So you add and subtract this term, right? So this is this term added, and this term subtracted. So they add and subtract this term, and then once you have that, we have the additional terms like W transpose Sn minus 1 W. W transpose Sn minus 1 W is actually Sn minus 1 is what we have here already. So this is, maybe to make it clear, this is actually Sn inverse. So this is already defined, and that one, and if you multiply this one with from the left with Sn, you get an Mn here. You see here, you get the, also we get the W transpose Sn minus 1 Mn. So we get the linear terms in W's by rewriting this with Mn's. So this is note Mn definition, and same here. So you get this expression. So right. So then what we have here is we have one term that is this term that we end up with is actually this, right? That will be a Gaussian with the mean and variance as given. And then this is the other term doesn't have any W's in it, so that can be absorbed to the normalization factor. Remember, this is just proportional, right? Therefore, there's this proportionality. So this is the constant. So therefore, we have achieved the goal. What does this buy us? Like we have actually a little bit played with probability theory here. So we have actually converted the prior probability to posterior probability. Probability W given T. And we had done everything with probability T given W, which makes sense, right? That is the likelihood function. What is the likelihood label given what I have? This is the inverse. What is the likelihood W given T? And depending on what you are doing and using the Bayes theorem, these are of course closely related. So this allows you to explore this relationship using the Bayes theorem. Right? That's the key here. That's the key insight from Bayes theorem, right? They can convert it to each other. And we have seen this relationship with maximum likelihood map, the flip back and forth relationship using the Bayes theorem. I think this is good in terms of following up what's going on. You should be able to follow this at least. All right. As we did. So that's kind of the relationship with this, and then let's continue with the next step, the loss functions for the regression. So they can actually write this loss function in a general way as an expected loss. Because we have adopted this probabilistic view, the loss is conditioned on this joint probability of xt, and then you take the double integral with respect to x and t themselves, and the loss function depends on t and y of x, right? T is the true label, and then the y is the predicted label. If you actually put L as the square loss as before, then it will be, this one will be replaced by this, right? And then if you solve for this expected loss, if I take the derivative of the expected loss with respect to y of x, partial derivative, I get the, this is just the straightforward quadratic optimization, right? I take the derivative with respect to y of x, I get this, and with the dt here, and then if you actually sum the terms up, if you take the integral of pxt dt, then you end up with p of x, and then that p of x multiplies y of x, therefore it's in the denominator here, so it becomes px y of x minus this equals 0, therefore p of x y of x equals this, and then to leave y of x alone, I can put it to the denominator, and the other term is t p of x t dt, so that is actually nothing but, if you actually look at this, by definition, this is the expectation over t, conditional average over t, the expectation of t given x, right? So that would be the regression function. What is the expected label given x, right? So that would be the y of x as we used before. So now I would like to go slowly to this bias variance trade-off we discussed before, and then starting from here with this maximum likelihood stuff. So actually, if we take this term and square term, loss term, right? My prediction should not deviate from the real values in the test set. I can actually subtract and add the term that I just mentioned, expected t given x, right? And then if I take the square, just do this scalar squaring, I get this term, then there's the cross term plus this last term, right? So this is this square term, which was here, right? And then when I plug it in, the integral is still there, and then integrating over t, this actually kills the cross term, so I end up with these terms. We had the double integral, I integrate over the t, and then I get with the that gets rid of the cross term, so I get these two terms in the expected loss function by doing this trick. The first term is about penalizes, this is a penalty function that I'm minimizing, right? So the first term ensures that our value y of x is the most likely label. Expected t of x as derived before. We did this before, right? So the second term is the variance of the distribution of t averaged over x. So there is this expectation, but then it's a variance, and then we get the average variance over the data set. So to clean up the little bit of the notation here, if we define h of x, which is expected t given x, this is what we have derived in the previous page, right? And then we can write it everything in terms of h of x, little bit cleaner notation. Then this becomes simply y minus h. Everything else is the same. This becomes h minus t. Okay, there's nothing else going on here. And then I go, if I focus on the first term though, y minus h, right? So that's like this first term here. Then conditioned on data. So we can also expand this, x given data, y of x given data, the new x, and then which was trained based on the data set I have, because this happens in the test set, right? So there's that conditioning going on. I can pull the same trick and take this quadratic term and add and subtract this y of xd, the probability of y, joint probability of y of x, and then given the data set, the joint probability, and take the expectation over the data. So and then rewrite the term, and taking the expectation with respect to with respect to the data, removes the last term, the cross term. So we end up actually again 2 terms out of this. So we take the first term, we had this only simple, what we are doing is we had this only, we have expanded, we have written this as a side activity, then we have expanded this square term into 2 parts. This cross term, when you take the integral, vanished. We ended up with this. Then we focused on the first term itself, and then the first term itself can be expanded into 2 pieces, and actually 3 pieces. Then one of them again vanishes when you take the expectation with respect to the d. Therefore, when you take the expectation with respect to the data itself, which makes sense, and then we do this, then we have these 2 terms that come from here. And we have the first term is the bias error, right? Given taking the expectation over the training data, how much of an error I'm making between my predictions and the likelihood, right? Function, and then that's squared, so it's bias squared. And the second one is the variance. And this was the first term, and then the second term in the previous one. Actually, this is a noise interpretation. How much, noise that is introduced to the, how much noise contributes to the expected loss. So we have this interesting. Then the long story short, I thought this is important because it's a very fundamental thing. It is not applicable to just linear regression. It's applicable to almost any method, including neural networks. The issue is it's easier to derive this for linear models like this. In the more complicated models, you may not end up with a nice analytical description like this. Expected loss is then the bias square plus variance plus noise. So you see, when we optimize my loss function in the regression, in supervised learning, it's actually a multi-objective optimization. There's a noise term, there's a variance, there's a bias, right? Noise term comes from the model. So depending on the model, there will be always some unmodeled stuff that I categorize as noise. Then there will be a variance and there will be a bias. And that's what we already discussed a little bit before, right? So you can have low bias, high bias, low variance, high variance. And regularization allows us to trade bias for variance and vice versa. So by actually, when we write regularization, we kind of have shown also the loss function was multi-objective. We try to minimize the bias, but we also we added a second term, and then these second terms actually connect to each other. So you cannot have everything at the same time. That's actually, given a model, there is always a fundamental trade-off between bias and variance. That's the main message here, and pictorially shown. So you can change the trade-off function lambda, the weight function between the multiple objectives. Remember, I was talking about multi-objective optimization. You trade them off by weighting the individual objective and sum them up. This is exactly what's happening here. So if you do regularization, you can, as you have done, explicitly choose that weight function. And if you if this is the original, right? Look at what's going on. Green is the ground truth. Red is what you are estimating. Here you have a lot of bias. You're making a lot of error, right? But its variance is low, right? Low variance, your estimates are consistent, but as you change your bias variance trade-off through the regularization factor, you change the regularization factor, that's your knob, you get better here, you increase a little bit of the variance, but now your bias has decreased, your mean estimates are pretty good, right? And then here you're doing even better as the bias, but now your variance has increased. So that's your model gives you a bit more shaky estimates that are not that robust. So this is another one with respect to errors, with respect to ln lambda, that's the trade-off regularization factor. And you see the variance decreases, bias increases. Bias square plus variance is the pink function, and that is a very good representation of what's going on with the test error, right? So it follows the test error there. So there's a sweet spot where you trade off, like this middle one, little bit. You give little bit of in terms of consistency. So you get some variance in your estimates, but you get pretty good in terms of bias. So you don't make, on average, don't make too much error, but you pay the price in a little bit of more variance, and vice versa. So this is very, very fundamental. And also another picture that I've shown, I duplicated here. All right? If it makes sense. So as I said, this is a good derivation that shows things for linear regression with the quadratic loss function and the expectation. We have the maximum likelihood type of probabilistic point of view, where you take the expectation of t, likelihood function t given x. We add it and subtract it and make it more explicit. And here we also make an expectation over the data itself. So then we have these bias and variance terms and then the noise terms. So we have an explicit derivation of the components of our loss function. This is taken from Bishop, so there's pretty good discussion about that in Bishop. I should put maybe a link to which page it is. All right. As I said, it's also more general to almost any supervised learning technique. The same thing applies to neural networks, but in that case, you won't be able to write these equations as cleanly as this. Actually, you might, what did we assume here? Did we make a, yeah, we have made some probabilistic assumptions, right? Not all of them are probabilistic models. So maybe it's actually this is broader applicable than linear models. But not every model is linear, so that's the other thing. If you go to nonlinear models, this probably starts to give up at some assumptions. All right. Shall we continue? Maybe yes, a little bit more, and then we give a break. Any questions? Yep.
Can we use the cascaded model to solve this trade-off, like for the first stage? Because we want low variance and low bias. So for the first stage, we make the model to be low bias, and for the second stage, we make it to be the low variance.
I mean, okay, this is a very good question. The question is, can we actually address this trade-off by doing a multi-stage modeling process? Okay, let me give you, I shouldn't say anything wrong, because this is a very general question, and it's easy to give a wrong answer. So let's think about it together, right? So assume we do what you're saying. The combined multi-stage thing will be a model itself. So by doing multi-stage, actually, you are not changing the modeling process. You just implement it in multiple stages, but you can look at the whole thing as a model, even if it's a multi-stage model. Therefore, it doesn't change the fundamental. So you still will, that model will still have the bias variance trade-off. The other thing is, right, so it will still be a model. You just implement it in multi-stages. Yeah, but it won't. Like the combined model will be the model. So therefore, that you cannot have a shortcut like that. It won't solve it like that. But there is also, I should also say, not every model is the same, right? If you give it a wrong model, maybe you will end up with a very bad bias variance. If you choose a better model, then you can get a Pareto improvement, which means you can improve both of them at the same time. So there is also this model selection business going on. If you choose the right model for the problem, then maybe this trade-off will not be bad. I mean, you can improve both of them at the same time. But if you choose the wrong model, then you will get both of them bad, and no matter what you do within that model, maybe it will not work. So model selection is also a prior that we are doing, which we need to keep at the back of the head, like right model for the right job kind of thing. And that will improve both of them. But fundamentally, this is a very fundamental trade-off. So you cannot actually get both of them that clean, that easily, unless you have a really, really nice model that fits very well with the data. So that's here, for example, the model is very clear. The green one is the Oracle model. In real life, we don't know this green one. In this case, actually, if we have the green one, that's the perfect model. It will give us the perfect bias variance, the whole thing, right? It will actually be the perfect one, and then the only thing left will be a bit maybe noise if my observations are noisy. And if my observations are not noisy, then it will give the perfect solution. But finding this green one is almost impossible in real life because you don't have that ground truth. And it's not always as simple as this. And because you don't know, you always build a more complicated model. And more complicated model may increase one or the other, right? We go back to this overfitting business as well. So you make a more complicated model which may help with maybe you see this is a bit maybe more complicated model which may help with the bias, but your variance starts to give in, and vice versa. Then you choose a simple model, this is almost linear, but then you get a big bias error. So yeah, it's a kind of an interesting thing, and then that's better to also experience this, through the experiments. Also, that's but excellent question. Thanks for that. So logistic regression. So that's really a good topic. It's an old topic, and Bayesian inference. Before machine learning was like statisticians doing, and then the inference people were doing the learning stuff, and they adopted a very, very probability-oriented point of view. The probability theory is not data-oriented. You should also think about that a little bit. Like the data science wasn't invented by statisticians. Between you and me, and don't quote me on this, I have seen a lot of I was in a statisticians meeting by chance, and they were really complaining a lot, saying, "Oh, these computer scientists have taken over our field. We should have done this." But they were not doing it. They were just writing probability distributions, P of X, and writing mathematics based on that with a deductive method. They were not doing experimental, big data sets and so on. It was also historical reasons, right? Computers weren't that good, but they missed the boat a little bit, and computer scientists actually taken over their tools and all the atmosphere from their funding and so on. So they were a bit complaining about that, but I would say that's their fault. This is a very, very Bayesian and probabilistic approach to the classification problem. So let's look at this. It's still very solid, right? In terms of thinking, it's really useful to have these thinking structures in the head. So if we look at the probabilistic Bayesian approach to the classification, we have the data X and classes C, let's say 2 classes, binary classification to make things simple, right? What we can do is we can determine Px given C for each class individually. Given a class, what's the probability of X being a dog picture, probability of X being a cat picture, then the dog and cat will be the classes, right? C1, C2. And then I can actually use Bayes' theorem to find probability of C given X. So if I give you a new picture, is it a dog picture? Does it belong to class 1 or does it belong to class 2? What's the probability that it belongs to class 1 and what's the probability that it belongs to class 2? So this is the whole story here. So if I write it PC1 given X, then actually this is right, you see that's the joint probability distribution. I wrote it through the product rule and the conditional probability. And then the bottom line is actually nothing but P of X, right? Then P of XC divided by P of X, that's the very much definition. I just opened it up. Now, this is a really nice trick. Actually, you can write it in this form, and it's not obvious, right? You need to define A properly. So here, if A is this, then this is the same as this, right? And, because this is ln, exponent minus, so this needs to be switched because of the minus sign. So PXC2, PC2 is in the up, and then PXC1, PC1 is in the bottom here. And because exponent ln, they cancel out. So actually you have that PXC2, x1, multiply, then reverse, you get the same thing. Huh? So you can actually check it. So this sigma is actually the logistic sigmoid function. And that's, logistic regression, as you can imagine, this is the thing that plays the role. So the logistic sigmoid function is actually defined as this 1 over 1 plus e to the minus a, where a has this interpretation. So you see, then you can use it directly for classification purposes, immediately for binary classification, when you have two classes. What are the properties of this function? When you write it this way, it's just a function of a. It is, if you, sigma minus a is 1 minus sigma a. And also I can invert it, a is the logit function, which is just the reverse of it. Ln sigma over 1 minus sigma. And this is the log odds of the ratio, or ratio of probabilities. Right, so the logit function a, which is this, but a is also this. This is the log of the odds of probability of x given C1 divided by probability of x given C2. If you have a prior equal probability, equal distribution on the classes, you can actually ignore them. Then you have this, ratio of probabilities. That is the a, and that is the logit function. But a can be also written in terms of the sigma, like that. All right. So let's do this next one. Maybe you can do it. While I rest my voice a little bit, and then we just show the things that were there in the previous slide. Let me switch to give you a better view of things. All right. And, It's good to exercise some algebra, I guess. Nothing deep here. The reason why I put this question is sigmoid functions also are used in neural networks. So it's good to be a bit familiar with these sigmoid functions. That was my main intention. Sigmoids are usually used, I will come to next week, in the last stages of the output stage of the modern neural networks, deep networks, for classification problems. So good to know a bit more about it. Shall we do it together? Yep. I think I'm supposed to ask one of you to do it, but anyway, maybe you'll help me, right? So there's the audience. We can start. We need to show this A relationship. One way is starting from the right-hand side. You know, the solution I have starts from the right-hand side, but I think you can go both ways because it's too simple. It's a simple thing. So we can write 1 minus sigma A, right? So we can write this as 1 minus 1 over 1 plus e to the minus A. But then that would be 1 plus e to the minus A minus 1 plus e to the minus A. These cancel out. You get e to the minus A divided by 1 plus e to the minus A. Well, actually, we can then multiply both sides with the, I love this. We never run out of space with this whiteboard. So e to the A, I multiply both the numerator and denominator with that. Then I get, what? I get 1 over 1 plus e to the A. No, yeah. That would be, maybe write it this way, e to the A plus 1. 1 over 1 plus e to the A. But that is nothing but substituting A with minus A. So we are done. Not much here. And the second part is the deriving the logit function. So that's actually quite straightforward. If we just take the inverse of a function. Sorry about that. So we got y equals sigma A, that is 1 over 1 plus e to the minus A. Therefore, we need to put A. We are taking the inverse, so we need to write A equals something. So that would be 1 plus e to the minus A equals 1 over y. Then I can write it this way. And then what do? I take the log, ln. Maybe I use the same color. ln of both sides, then I get the minus A here, and I get the log ln 1 minus v over y. And then minus sign log, it just inverts. So I get the A equals ln y over 1 minus A. But y was sigma, so that's the same as sigma over 1 minus sigma, but that's what we were looking for, so we are done. Yeah. So the logit, I will come to this also. The inverse is kind of useful, has an interpretation and use for the logistic regression point of view. Should we give some break? 10-minute break, then continue quarter past, or yeah. 14 past, quarter past, and then continue from there. Actually, you asked me that question during the mid-semester test consultation, right? Yes. I have an answer.
Okay.
But it is, I need to post it. So the thing that you were asking was notation was confusing. So you were asking about this dot product. In independent, linear independence.
Oh, yes.
Yes, I have an answer to that. Maybe when you come to the consultation, I'll explain to you.
Okay.
And I need to update the slide. Yeah, the slide was misleading. There was a typo on the slide, which made you confused.
Yes.
Then I made me confused as well. I need to update that slide too. Actually, it's very simple explanation.
Okay.
So it's just we got confused. So that's. I have the answer to that. So you stop by and remind me, okay?
Yeah.
I'll do
Thank
that.
you very much. I have a question about two main questions. About this part, it's conditional data D.
Yeah.
What is data D here?
That data is the data set.
Oh, data set.
Yeah. Now, notice that we are writing this loss function on the training set, test set, right?
Okay. It's
And
on
then-
the test set.
And this whole loss is done at the test set. And then no, I shouldn't say that. Like when we train, we optimize on the training set. Okay. When we train, we optimize on the training set.
Yes.
And training set is the data set.
Training set is data. Oh, okay.
Yep. So we train on the data set, right? When we find the W's,
Yes.
minimize the loss, we use the data set training set. That's data set is the training set. That's why it's conditioned on the data. Given the data, I find my W's.
Okay.
Different data will give me different W's.
Yes.
And that's
So
the
different
best
training data set gives different W.
possibly.
Possibly.
And we are doing our best to optimize with respect to that. Right? Okay.
Yes. And about this part, I completely don't understand this part.
Yeah, this is a model, right? The original is the green.
Oh, original is green.
And then you have different models that kind of, this model has a large bias but low variance.
Low variance.
You increase the variance
Okay.
and then bias decreases, error decreases. Here error is perfect but you have too much variance.
Oh.
There's a sweet spot. And then how do you tune this? You can do it with regularization. I took it from Bishop's book from the regularization section.
Yes. Can I have one more question? When we say bias, what does that mean?
High bias is this big error in the mean.
Oh,
Big error in the mean.
big error.
Just like the equations, previous page equations.
I still can't understand this part.
Yeah, well, you should check the book as well. Like, have a look at the book. If not, come back to me and we can talk.
Okay, so
But like,
the
what-
book
what-
is.
Wait, here it is actually. The equations are here, right? So the terms here. This is the bias term. This is the noise term.
This is-
So like, look here. From here we go here, and then this is the bias term.
Oh,
Yeah, like this is bias. My estimate versus the h, which is the likelihood, and then the variance is the expected square, the definition of variance.
got it. Thank you.
All right? Okay.
I was gonna, this is probably a silly question,
No,
but
no.
I got a bit confused when you were saying this. I'm not sure if you explained it, but
No, it's given, right?
so yeah, T.
I'm adopting the Gaussian model and then multiply it over the IID.
Yeah. So how does this the same term as this one?
I mean, I just skipped the beta here. That's the notation just.
Oh, so it's just kind of leaving these two out.
Yeah.
But so you can just do that. That's like it.
You shouldn't too much, but I was taking them from different places.
That's
and
okay.
so,
Yeah, I just wasn't sure. So
Yeah,
that's.
I mean, it's better to be more explicit usually.
Yeah.
Yeah, but you see, this is all appearing. The W is appearing, beta is appearing. So
Yes.
I mean, you can put a lot of stuff there. Also, given a lot of stuff, right? We
Yeah.
assume a lot of given stuff. People usually kind of get lazy about it and focus on the W, like main thing, which is W here.
So this is more of a question about the notation. So does this necessarily mean it could be either t given x or t given w or t given beta, or is it t given all of those?
It should take given all of those. The thing is, what are you doing with it? which ones are kind of not coming to the discussion.
Okay.
People are then lazily skipping those.
Okay.
In this case, for example, it's all about W here. Then you focus on this. If it's all about X, then these kind of are fixed, then you don't take them into account. Yeah, in life, usually things are conditioned on multiple things.
Yeah.
It's a bit of a notation laziness thing.
Okay. Yeah, I just couldn't find this here, so that's why I was a bit confused.
But yeah, does it now make sense?
Yeah, it makes sense. Yeah.
All right,
Makes
very
sense.
good.
And is your only consult on Tuesday afternoons, or is there morning? Or?
Not really. I prefer one day only.
Yeah. Yeah.
Does that fit?
Yeah.
To your
try
schedule?
To the next one. Yeah.
Sure, of
Yeah,
course.
yeah.
Yeah.
Thank you.
Just one we divide the data from 2 numbers, and then we want to predict the integrated.
Yes.
Yeah, and I'm just confused about.
But this
the
is
four walls.
this part is this part,
Ah,
not the future data part.
okay.
So you see, I'm here dividing the training is the white ones and the test is the red one.
Okay.
And then you know, the one way to do it is what you do also in sklearn, right? In the workshop, it automatically selects randomly 25% out of the whole thing, makes it the test set, and 75% becomes the training set. Here you do it a bit more like a organized fashion. You kind of select these 4 chunks that are not overlapping and then do multiple runs, k-fold validation. You can do also 10-fold validation, right? You can just divide it into 10 pieces. There are multiple ways of it.
So
You shouldn't do 10-fold because like here, if you do 4-fold, it's a 75-25 ratio. That's kind of a well-accepted ratio of training to test set.
okay.
Usually we want a kind of a balance between them.
And the last question is here.
Also, it takes forever to run each of them.
Yeah.
You're solving the problem 4 times. It takes time.
Yeah. And I think
This is high variance, you see?
Yep. Yep.
And this is low bias.
yes. And lines here is this line is more smooth, and
Yeah, this is less variance, but then you do a big price in the bias.
that's why I want to know. It looks nice, but it matched well.
Yeah, but then it matches well, but this is the mean. Individual runs may have a lot of variance.
So that means if we have the low bias, then we make match well.
So, but then individual ones, runs, may have variance. So that means day to day you are making more mistake. Only in the mean you are getting better. So like the mean of a sign goes to 0, but you are still fluctuating a lot. It is like that. Here you are fluctuating a lot. And as you say, smooth is better. It's consistent. But then you are making a big mistake on average. Does it? Okay.
One more question.
Okay.
About this part, when we do the derivative on yx, why we don't have dx? I mean, I understand this part, but I think we lost dx here.
Wait, what is that?
Just this. And we can move it into here. So we get y(x) minus t here. But where is dx and this? Should we have one more integral symbol? Dx. Okay. Or it just should be like that. Without dx and this is
Yeah, I mean actually that's the thing. I think if you make inside 0, then the whole thing will be 0.
okay. So you mean when we have 0 here?
That will also make the whole integral 0.
Okay. So we just need to count this part.
Like also 2 doesn't play a role, for example.
Sorry, which one?
Two doesn't play a role either. Two
Oh,
times.
yes, that 2 and this integral symbol and dx, they don't play the role. in
Because
this
we make inside 0.
Okay, yeah.
I think that's why, yeah.
Okay, thank you.
Yeah. Makes sense, right?
Yes.
Yep. Oh yeah, we should start. Time is running. Okay, now let's go back to logistic regression, right? So where were we? We have covered this part, and we played with the logistic function itself a little bit, sigmoid function. Now let's go back to the whole logistic regression stuff, the main derivation. So, we have this likelihood function, probability of given. Actually, we can use a linear function, linear model. We can embed a linear model to this whole thing. What we do is we have this probability of given x. What's the probability of it belongs to a class 1 or 2? Let's look at the binary case as a special case, but it also applies to multiple classes. And then if we choose the logistic sigmoid acting on a linear function of the future vector, so we can actually adopt the linear model as before, we can write A equals W transpose phi of x, right? We choose a phi of x kind of a transform, and then, not kind of a, it's a transform, and then create a linear model of this basis functions, right? So A becomes that, and then I can write this likelihood of probability of this belonging to class 1 as this. Now, then the likelihood function we want to maximize, if we want to find the parameters W here, if we adopt this model, we fix the phi, that becomes our hyperparameter or meta parameter and model that comes with it. If we do this, we want to find the W, right? In the logistic regression. And we can use a maximum likelihood approach to find the W. We need to write the likelihood function. What is the probability of label T given W? And T could be class 1, class 2. That would be with the IID assumption for each data point at 1 to n, probability of this belonging to the C1 with the label, but it cannot be belonging to the other one. So that's that becomes the likelihood function and product over this. Or you can write it this way, where we have the yn is this, and A is the difference here is we are making A equals a linear model, right? So we adopt a linear model here. So we can again take the log in the maximum likelihood when we optimize the likelihood function with respect to W. It's an unconstrained optimization. We minimize this and the expected value of W, which is this as I've written before, and taking the derivative using this property. There's just a straightforward from the property of the sigmoid function. We obtain an error gradient, and that's how logistic regression usually works. We can use an iterative method to find the W that minimizes the error and maximizes the likelihood. So the error comes from the maximum likelihood formulation, and minimizing the error, I can write a basic gradient descent to minimize that error, and in terms of find the best W to minimize my error, which gives me the maximum likelihood. One thing maybe to note is when you take the derivative of sigmoid with respect to its argument A, and in this case A is this, right? But if you keep it at the high level with respect to A, its derivative it can be written in terms of itself. So that's kind of also computational convenience, brings some computational convenience to the problem. So kind of an extension of what is done here, I have kind of skipped it, how to take the derivative. The next question actually looks at that. How do you take the derivative of the multi-class case? The derivation for the single class case is already there. Here the multi-class case, we want to derive this like this. So let's do that. And also gives you an idea how will the multi-class case work. It's not always binary classification. With logistic regression, you can also do, n classes. Like I was giving the famous example of the MNIST digits. Then you have 10 classes, right? Each picture belongs to one digit. Or it could be a finite alphabet, like then in the highways, tollways, the readers have to read the plate and then charge you for passing through, right? So that's also a classification recognition problem. Very classic image recognition problem. So we have, maybe make it a bit bigger. So we have show that the derivatives of the softmax activation function in multi-class k-classes logistic regression, right, with respect to the activations which are given through the AK through the linear model here with the individual WKTs are given by this. Notice this is the softmax function. I must have mentioned, I remember mentioning softmax before. So this actually is a nice way of writing max, but it is soft, so it is nice because you can take the derivative. And as you take the limit, it becomes closer to the max. So we have so we just write it down. So there isn't actually much to be done here. The derivation. Let me do it quickly. We can take yk to ak. What would be the yk to ak? For then with this, so we have e to the ak, so this will be the partial derivative with respect to ak, partial with respect to ak of e to the ak divided by sum j e to the aj. So of course one of them is also k, so actually I have both the numerator and denominator, so we need to adopt the product rule, basic calculus and partial derivatives. So if I take the derivative with respect to this, it will be it will be itself, right? So it will be e to the ak times 1 over this j e to the aj, and then the derivative with respect to the denominator, which has also an a kth one included in the sum, j sum. So therefore, when we take the derivative with respect to the kth one, then it will, all other terms in the sum will be 0, but the kth one will be e to the ak, e to the ak, yep, and then that will be the comes to the denominator. So the first, this will come as the e to the ak, the first term, and then the denominator taking the derivative of say x 1 over f of x is f prime of x f of x squared minus, right? So that's the basic equation I'm using here. So that derivative comes up, so I have 2 of these a to the ak's, so this is squared, and then the denominator squared will be then the sum j e to the aj squared, right? Okay, and then this means I can write it actually in terms of y, and that would be this is then yk minus yk square, or because yk is this, so we should maybe clear this up where this does come from. So this is here, right? And then, or another way of writing this is yk1 minus yk, right? That's for the kth one. And for any j not equal to k, for j not equal to k, then I take the yk del aj, or maybe I should say I, I not equal to k, I, because I use the j for the sum, it becomes a bit confusing. And in this case, it doesn't appear in the numerator, it only appears in the denominator. So I only have this e to the ak, e to the ai, divided by sum of j e to the aj squared. And that's nothing but, you can write it in as minus, there's also minus sign because of the same thing, minus yk and yi, right? So I wrote it in terms of, yeah, but then it will not be matching to the jth one, so I should use here another dummy variable, L for example, and use j here, j not equal to k. This will be j, this will be j. So we can actually write this in terms of, you see this is becoming a conditional function. So del yk over del aj equals yk1 minus yk and minus yk yj if j not equal to k, so j equals k. And the shorthand for this is the indicator function thing that's going on here. Yk, use an indicator function kj minus yj, and just a shorthand because del kj equals 0 if j equals not equals to k, and 1 if j equals to k. This is just a notational shorthand. So therefore, this is just a, say, instead of writing it like this, you write it like this, because then if j equals k, then it's the first case, j equals k, therefore it's 1 minus yj is yk, so it's, you have the previous result, which is this line, and if j is not equal to k, then this is 0, then you have the same minus yk minus times yj, right? And that is the second term, right? It's just a notation. Simply notation. Right?
When you did the derivative of the 1 on fx thing in the box, applying that to 1 on the ak pretty much is...
Sorry?
You forget to take the coefficient of like the ak,
What? No, this is just x. I mean, this is a general formula.
if you scroll up a little bit, it's not right there.
I'm doing the product rule here.
Yeah, so when you take the derivative of the denominator,
No, I'm not doing this. I do product rule. First, I'm taking with respect to this, and the 1 over remains the same.
for the second part, when you do it with respect to the bottom half,
Then e to the ak is there already. The bottom one will be then
if you take the derivative of e to the ak, shouldn't it be
E-
ak times e to the ak?
no e to the ak with respect to ak is e to the ak, the derivative. AK is the, we are taking with respect to AK. So there is no, we are not opening up AK itself. I'm not taking derivative with respect to W. I'm just taking the partial derivative with respect to the AK. Yeah, that's from the calculus, partial derivatives. Yeah. All right. So let's continue. So we have this. It also shows how. So if you have seen this, then you can also take the derivative here and get the results yourself as well, verified results. So, okay, so we need to actually move on a little bit with the last word on the logistic regression. So I actually should have put maybe this earlier. This is how the logistic function looks like. And actually, depending on how you write it, actually you can parameterize by a beta, and 1 over 1 plus e to the minus x or minus beta x, right? For beta small, it is a softer transition, and then beta, large, it's a much more fixed transition. And as I was saying, as beta goes to infinity, then you get a step function, right? And just like softmax going to max, sigmoid goes to a step function. Historically, remember, no, I haven't covered it yet, but the oldest neural networks were using step function at their output. The advantage of sigmoid over step function is you can take the derivative. And that makes a lot of help in the back propagation, right? You train it with the derivatives. As you can, now that you know optimization, derivatives are fundamental to any gradient descent methods. So if you are minimizing loss functions and you have anything like this, actually in this case we don't have to talk about the neural networks, like when you want to minimize, you maximize the likelihood or minimize the error that comes from the likelihood, right? I put a minus sign in front of it. You can use a gradient descent method for that. And for the gradient descent method, you take the derivative of the sigmoid function. And the sigmoid, you can take the derivative of the sigmoid in a very convenient way, pays off big time here. If you use a simple step function, how are you going to take the derivative? That's the issue there, right? There are some notes here, like with maximum likelihood, it can be logistic regression can overfit data sets. Then you may need to use some regularizations or map if you have some prior knowledge on the parameters. One good advantage over non-probabilistic classification is it gives you a kind of a probability value in addition to the binary. Like we were discussing in the beginning with the linear regression methods. Like it says, this point belongs to this class with probability 0.8, or this point belongs to this class with probability 0.2. This is like the weather forecast. So you don't want to be very precise. You don't want to say it will rain tomorrow. You just say it will rain tomorrow with probability 0.6, right? So that's a classification problem. You can look at all the weather data and make a prediction for tomorrow whether it will rain or what, right? And then it's much better to say, okay, it's going to be raining, but with probability, right? And then that gives an advantage over non-probabilistic methods. But it's not a very popular method these days. Like most of the time when people do classification these days, that's not the go-to tool for that. It has other advantages. You can actually do root cause analysis a little bit with logistic regression. Which factors, using the logit function, you can use the Bayesian theorem to kind of which factors play the role in my decision type of thing. Again, non-probabilistic tools don't have that property that much. In that sense, one shouldn't dismiss it, and it's a fundamental tool and connects things together nicely. So that's why I thought it would be appropriate to include. All right, now the very important topic of kernel methods. This was the very at the center of classical machine learning in the 90s until the last part of the last century. And then kernel methods and support vector machines were all the craze during that time until early 2000s, before the deep learning stuff took over. So this is here I will go through a very the fundamentals of this and try to give you the insights how the kernel methods work. So here's the deal. Let's go together, right? So we have a data set with input data. We have the training data and the outputs, like labels. So this is a supervised learning problem. Each data point has a label. It could be binary or multiple, or it could be regression. For a linear model, let's stick with the linear model. Let's simple linear model. No, not even phi of x. You just have a linear model as a dot product, W times X, right? And then we want to find the best W's that fits the training data, right? So if we have a linear model like this. So now, here's the thinking. It's a bit linear algebra here. So the null space of the data set that I have at hand, training data set, contains perpendicular X perpendicular such that these are the dot product of these with the data points are 0 for all the data points that I have. That's why it's the null space. So those actually the dot product of those with the data points are 0. So that means actually if I write it this way, I take the W star plus the perpendicular ones. So that is, they don't play any role, because then when I multiply this with this, I get this. When I multiply with this, by definition, I get 0 because it's in the null space of the data set, right? So this is a trivial result, but it will be useful. So what it says is adding a contribution to my ideal parameters outside the space spanned by X has no effect on the predictions on the training data X. So if I add these additional ones from the null space of the data set, they don't play a role. But what does this mean? Again, it's very simply, this is very simple. There's nothing mysterious going on here. This means we don't need to consider contributions to W outside of X, which is kind of a tautology, right? So we derive the W's from the X. Therefore, anything that is at the null space of X will not contribute to the W's, which it's intuitively, a DA type of a statement if you think about it. Because I derive the W's from the X, and anything in the null space of X will not contribute to the W's. So, but that is an implication. So we can write then the W's as a linear combination of the data points with these coefficients A are called the dual parameters, right? So basically when we write the dot product then, if we adopt this, because we agreed on this, right? So we can write it this way because anything that is not belonging to outside, they will be in the null space of X, and as I said, they will not make any difference because they are dot producting to 0. So if I write this combination then, which is the linear combination I mentioned, the linear model, very simple linear model without any transformation of X, there is no phi of X here, we can simply write this W in terms of this, and you see we have this term A's coming in as the dual parameters, and I have this interesting expression here. We can now generalize, and this is not true only for the W transpose X, but we can also write it in terms of the phi of X's in the space spanned by these, right? Phi of X1 to phi of Xn, which is all my training data points. So some of the A's will be 0, some of them will not be 0. There's a lot of duplication here. Don't think about the computational aspects yet. It's just a general mathematical statement. If I write it this way, then I make a linear model out of it. You see, what I end up with is this expression, which is immediately follows from the definition. But this expression is, interestingly, we have the phi transpose and phi transpose xm, phi of xn. These two, I can combine them in a function k xm xn. Right? I can do that. There's nothing, again, mysterious going on here. But what we end up with, this is one way of motivating the kernel function. So I call this a kernel function, k of xm xn, which is the phi of xm transpose phi of xn. Right? And this will be like a matrix, kernel matrix, because we have finite number of data points, m, n. So I have this kernel function calculated. So the linear model can be expressed in terms of a kernel and these dual parameters. It will become a bit more clear step by step. All right? So until now, I haven't done anything other than saying W's can be written in terms of the data points. Anything, any contribution to W's from the null space of the data set will not make any difference. Therefore, I can write it this way. When I substitute it, I write it this way. And I can generalize it instead of the linear model like this, as I was doing before. I can write a linear model like this, as I was doing all the time today. And then I will end up, instead of this x transpose x, I get a phi of x transpose x. But then I can combine the two as the kernel function. So here's the thing. Why is this interesting? Is still not clear, right? I haven't told you why this is interesting. So this one way is defining this mapping phi of x, as we were doing, right? We have used phi of x, for example, the polynomial, and then we did the polynomial regression. But in this case, my model actually is not depending on phi of x alone. It is phi of x transpose phi of x. So the kernel function is defined by this combination, right? That is the trick. The kernel trick is we can't choose the kernel function directly. I don't need to choose the phi. I can choose k. And that is interesting. So I can choose a k that doesn't even decompose to phis. Or phis could be very cumbersome, but I can have a very clean k. As long as k is a valid kernel function. So without going too deep into the math, a necessary and sufficient condition for a function to be a valid kernel is that this Gram matrix that I've defined, the matrix with k, xn, xm, over the points, the data points nm, is positive semi-definite for all x. So for all my data, if the Gram matrix, the kernel matrix is positive semi-definite, doesn't even need to positive definite, then that's a valid kernel. That's a good result. And then here are some example kernels. So it could be linear kernel, which is exactly what I did in the previous page. It was xm transpose xn. You see that's a linear kernel. Everything is linear. Of course, things are more interesting when you have a polynomial kernel. The most widely used is the Gaussian or RBF kernel. This is the xy, kxy is like this, with a sigma square. That's a meta parameter, right? And the Laplacian kernel. Now, you see, I'm not defining phi anymore. I'm defining k. That's the important thing, very important thing to notice. I don't care about phi anymore. I just care about the k. So I'm transferring the whole thing to a new space through this kernel transformation. And I don't even know I don't even have to know the individual, the transformation that I'm making. I only need to know I'm taking the x's and transforming them to phi of x, right? Of course, if I know phi of x, there's no problem. K is just phi transpose phi. That's done. But because I'm only using the phi transpose, phi and phi transpose phi multiplication, the dot product, right? As long as I have a kernel function that gives me the dot product in the transform space, that's all I need to know. I don't even need to define the transformation itself. That's very powerful and interesting, in my opinion. So you only need to know the dot product in the transformed space and you're done. And the kernel function defines that dot product, you're done. You don't even need to think about where am I transforming this. That brings a slight mystery too. We will discuss why this thing is working. Because I'm doing a transform, I don't even know what transform I'm doing. I don't even need to know phi. I only know the dot product in that transform space. And it's good enough for me for the model. So some nice visualization here. We have the polynomial basis functions. They look like this. Gaussian basis functions, they look like this. And sigmoid basis functions. And with respect to x equals 0, in one dimension, that's how the kx0s will look like. These are defined as kxy, right? So the kernel functions are defined as kxy. So if you put the y equals 0 and one-dimensional version, some nice visualizations how these dot products look like, the kernel results, and the basis functions, how do they look like? So there is one example question which can help a little bit to what is going on. I think this is a nice question. Let's do this on the way. It gives a bit more insight. Otherwise, it becomes way too abstract, and it's actually not too bad in terms of this whole topic isn't that complicated. The nearest neighbor classifier, which you have used actually in workshop 2, right? Because you were clustering and then choosing the closest ones to the cluster belonging to the cluster, that's a nearest neighbor classifier. Assigns a new input vector x to the same class as that of the nearest input vector xn from the training set, right? And the distance, as we were discussing in the unsupervised learning, distance can be Euclidean metric, which is what we have here, right? By expressing this rule in terms of scalar products and then making use of kernel substitutions, formulate the nearest neighbor classifier for a general nonlinear kernel. Yeah, this question I haven't chosen it as a nice exercise question, but more for its explanatory power. It's not a very well posed question, but let's not worry about that. Let's solve it together. So we want to define the distance function, right? And that is already given, Euclidean 1, x minus xn square, right? Norm square. And we can write this in terms of this, right? These are vectors, so x minus xn, transpose and x minus xn, right? That will give me what? I multiply the things, so x transpose x, and then I get the xn, that will be plus xn transpose xn, and then the two terms that come with the minus signs are they are dot products, so I can write the transpose in any case in different ways. So I can write it in this way. Maybe I should write it this way, right? Then people sometimes get confused. In reality, this is this 2 times dot products, right? The dot product is either way fine. So remember, we have people keep asking me, so that's good to write. Right? So let's put a bit that fat dot to here. So that's the dot product. Now, what the question is saying is actually this is the linear version. Can I actually create a nonlinear kernelized distance metric? Yes, we can pull the same trick as we did in the slides. If we write everything in terms of the kernels, we can write these dot products in terms of kernelized dot products, right? I can take these dot products and move them to the transformed space by using an appropriate kernel function. The kernel function will give me the dot product in the transformed space. So how do I do that? I simply write it as kxx plus kxn xn minus 2k xn. Here we go, done. So as long as k dot dot is a valid kernel. So now all these dot products have been kernelized, so that means I have now a nonlinear, then maybe I should say it clearly, I can define sorry, I can define a d k, let's parameterize it, xxn, a kernelized distance metric. So I can use a nonlinear distance. Instead of using simple Euclidean distance, which will give me the Voronoi tessellation, I can actually use a nonlinear distance. But to do that, you see, the nonlinear distance, I can simply use, instead of the dot products, I use the kernel dot products. The kernel function gives me the dot products in the transformed space, and if that transform is a nonlinear transform, suddenly my distance metric is not, I don't have Voronoi tessellation anymore. I have something different, and I think this one, is it Voronoi here? I think it's still Voronoi, right? So, but you can have a distorted partition with the nearest neighbor classification, or and so on. So that's the kernel power of the kernels. So you can actually use the dot product, and we will use it in the support vector machine much more efficiently. But this is a kind of a nice, interesting side question, kind of introducing you more into the world of kernels. Now let's continue a bit more, because I'm fearing I'm falling behind. Maybe this one. So now I can continue the same idea and apply the same idea to linear regression, right? Dual representations in the linear regression. How do I represent linear regression with regularized sum of square error in terms of the kernels? So this is a regularization factor, right? Ridge regularization. So then we have a square error and a linear model as we have here, phi, right? We have done this before. So y equals then W transpose phi of x. So this is an unconstrained, nice convex optimization problem. In W's, I can take the derivative and find it, right? Which I have done. And then once I write it down, I can write it in terms of the, you see, when I write this down, I end up writing it in terms of the phi of xn. And then, remember, we called these an, these dual variables. So actually, I can define these as an and write W as a phi transpose times A in a matrix form. Defining this transpose matrix through this is a matrix multiplication. Appropriately defining it through the column or row vectors, right? Depending on how you define this phi, capital Phi, as row or column, then you need a transpose or not transpose. But let's stick with the definition given, right? And an, as I said, is defined by this. So you see, this is the same thing I was discussing before. I can write the W in terms of the phi of x's. And xn's being the points in my data set. This is sum over n equals 1 to n in my training data set. So we have connected the dots in a sense. We have done this before in a bit blind way. Now the optimization result, you see this is in terms of the dual variables. If I substitute this into this, actually, and then use the fact that y is this, here this is, y is this, t is given, t is the given labels. And then write open the square here and substitute each of them. For example, W gets substituted here, you get this expression, you see? This gets here. Then I open this one and then take the sum. I end up with this sum is already embedded to this matrix multiplication. Therefore, I end up with this nice long expression. This is nothing but the same as this, right? With the substitution being done, the sum disappears because it's embedded to this matrix multiplication. But we observe something very interesting thing here. This comes from the phi, right, directly. And that is related to the Gram matrix, actually. If you write it down, this times this transpose is the Gram matrix of the kernel, right? K, X, and XM. So if we write it in terms of the kernel matrix, then the individual phi's disappear. Again, we come to the same conclusion. So I can write the linear regression in kernelized form in terms of the A's, right? Which will give me W's directly together with this in terms of the kernel function. So all I need is then the kernel matrix. So I write this down, and minimizing JA by setting the gradient to 0 yields the solution A is this. So it is again in terms of the K. And substituting it back, now I can write Y as W transpose phi of X, which is A transpose this matrix times phi of X, but this is K of X transpose, and this inverse of this Gram matrix and the T, which I know already. The Gram matrix, the xn's I also know, X I don't know, X is the input, so this is the new X. And then you see new X depends on the previous axis through the gram matrix, the kernel matrix, because of this relationship, and then k of x is defined as this vector. So the whole solution doesn't require any phi of x anymore. So I've done everything in terms of the kernel. Again, the same kernel idea. As long as I know the kernel function, I know the dot product in the transformed space, I don't even need to know the individual phi's. So that's the main idea of the kernel function. So you kind of do this transform to the kernel space. Maybe I should have put this earlier. There is this interesting slide. I put it maybe too late. But the kernel trick, maybe I should have put it earlier. So the kernel trick is this. Because I talked about this transformation to the new space, right? And you might say, where does this help me? So let's say you have this problem where you want to separate the blue points from the red points. In 2 dimensions, this is the problem, and you need to kind of draw a nice circle around it. This is not a nice function. It's a complicated nonlinear function, right? In this case, it's a circle, but it could have been even nastier. But if you take this problem in 2 dimensions on the right-hand side and transform it to 3 dimensions, right? I mentioned the kernel through the phi of x. I make a transformation. You see, in 3 dimensions, this is a trivial problem because the original data was looking like this in this case. Not always it looks like this, but original data was, now that I have transformed, the data looks like this in 3 dimensions. A simple linear hyperplane, you see that I cut it into 2 pieces. So if I want to do classification in the kernel space, all I need is this green surface instead of a complicated nonlinear line in the original space. And the kernel function gives me the dot product in the kernel space, and then the dot, as you will see, that's all I need to kind of solve this problem. And that's the kernel trick here going on. So I will come to it tomorrow. All right, so that's the power of the kernels. So you can, we will see it even maps the simple problem to an infinite dimensional space, and then does the classification in the infinite dimensional space. Then the result comes back as we discussed, right? The whole result we were talking about here, your result is in terms of the kernel functions and matrices. But this kernel might be mapping things to an infinite dimensional space, which it does in certain cases, and that may help things a lot for classification, separation things, as I've illustrated. All right, so yeah, thanks for your patience, and see you tomorrow.